small lecture before lunch, and I know it's going to be a good one. It's a particular distinct pleasure for me to introduce the next speaker, who's Elena Luca, a former student of mine, and very proud of her. She left me to go to San Diego, which I figured was as far away from me as she could get. And now she's actually here at Cambridge as a David Crichton Fellow. So good for her, and she's going to talk to us about viscous flows and channel geometries.
Thank you very much. Thank you very much to the organizers for giving me the opportunity to give a talk in this workshop. I will be talking about viscous flows in channel geometries. Okay, and then so let's start with the motivation of our work. So there's a lot of interest in the microfluidics communities in trying to understand flows in small scales. Especially, you see that many flows are modeled in these channel geometries, which have like a polygonal shape. So, for example, we're interested about the sperm locomotion in the female reproductive tract, and trying to model the shape of this geometry. We consider these flows in these small geometries. So we're interested to find new methods to solve viscous flow problems in this kind of geometries, or also having boundaries described by a polygonal shape, or also described by circular boundaries. So just go back. So I would just like to show you some videos where these things appear. So I found these videos on YouTube. So this is sperm in the female reproductive tract, and basically you can see that because of the geometry, these small particles they approach the boundary and take advantage of the geometry to move around this viscous fluid. To show you, this is again another example. So these are red blood cells, which again are moving in these complex polygonal or circular boundary geometries. So what we would like to do is to try to find new methods for modeling these problems. I think I have one more short video where you can see again red blood cell moving in this channel geometry here. So you have this change of geometry. Okay, let's go back. Yeah, so what we'd like to do is to try to model these flows. Okay, so I would like to mention the classical methods for solving these viscous flow problems. And most people use boundary integral methods, which are can be applied to general geometries. Also, eigenfunction expansions. So eigenfunction expansions depend. Their use depends on the geometry that we have. For example, if we have like a parallel boundaries, then we can use eigenfunction expansions. Transform methods against Fourier transform. For example, if we are interested to solve problems in a channel. Mellin transform in corner geometries. Wienerhoff method if we have mixed boundary conditions. Method of images, also bipolar coordinates. So I should emphasize that not many people have used complex analysis tools to solve viscous flow problems. And I mentioned some names here, so most of these people are here in the audience. And the thing is that the governing Stokes equations are not conformally invariant, meaning that in general we cannot use conformal mappings. But I should emphasize that many boundary value problems have been solved using conformal mapping techniques. So the progress can still be made. So in this talk, what we would do is to present new transfer methods for solving problems in much more complicated geometries, where the boundary could be polygonal or also have a circular shape. Okay, and although our focus will be viscous flow problems, I should say that the techniques apply to plane elasticity for incompressible solids. Okay, so this is the outline. I'm going to, since we are a complex analysis workshop, I'm going to present a complex variable formulation of Stokes flows. Then I will introduce the unified transform method, also known as the Foucault's method, and I will show how one can use the method for solving problems in polygonal and also circular domains. So this is work I did during my PhD with Darren Crowdy, and then I will proceed to present new problems that I have worked with Stefan Llewellyn Smith. These two problems here. So this basically channel flow problems, and then I will mention this last problem, which is motivated by biological applications. Again, okay. So we have the governing equations for viscous flows are the Stokes equations, which are given here. P is the pressure, mu is the viscosity, and U is the, so we're considering two-dimensional Stokes flows. So, and U is a two-dimensional velocity field. So what we'd like to do is to try to analyze the problems in complex variables. So what we do, we introduce this real function, the stream function psi, because the flow is, since the flow is incompressible, meaning that the velocity components U and V can be written in this form here. So next step is we take the curl of the Stokes equation, which gives this expression here, where this omega here is the vorticity. So next we also have the kinematic relation, which means that vorticity it can be expressed in terms of the stream function like that, and combining this expression here with this expression here gives us that psi satisfies the biharmonic equation. So yeah, so now we express this biharmonic operator in terms of complex variables, and if we do that, then we integrate 4 times, because it's like a 4th order, and we get this general solution can be written in this form here, where psi is the imaginary part of z bar of f plus g, where these two functions, f and g, are analytic functions. They can have isolated singularities to model flows of interest, but we will think of them as analytic functions. So the idea is we are given a Stokes flow problem. If we can find these two functions, f and g, then if we can find these two analytic functions, f and g, we can compute psi, and then compute the velocity components, and basically all the quantities of interest, the physical quantities of interest, like the velocity, pressure, and vorticity, and the fluid stress, can be expressed in terms of these two functions. So the idea of what I'm going to present in this talk is to find methods for computing these two functions, f and g. Okay, and the way to find these two functions, f and g, for the problems I will be considering is to use the unified transform method, also known as the Foucault's method, which was introduced in 1997. It's a method. This method can be thought of as a generalization of the Fourier transform method, since it involves simultaneous spectral analysis in both x and y variables. So we can think of the Foucault's method as a transform method in a complex plane. Okay, so now I'm just gonna give you show you the method, the unified transform method for polygonal domains. So let's see. So we have we consider this upper half plane, right? And we consider this slit of finite length, and then this point z dash along the slit. And then we consider this point in the upper half plane, which is in the interior. And obviously, we have that the argument of z minus z dash is from 0 to pi, which means that this integral here, like this exponential, can be expressed in this form here. So you can do the calculation, and it can be written in this form. So now let's consider the rotated slit. And then again, let's take point z dash along this slit, z in the interior, and then this is angle chi, and then a point alpha along the imaginary axis. So again, one can show that the argument of this quantity here is between 0 and pi, which means again that this integral here can be written has this representation. So so the idea here is that, notice that this is like the Cauchy kernel, right? This is the Cauchy kernel, and then this one as well here. And I should say that this new derivation of what I'm going to show in the next slide was introduced by Crowdy in 2015 for Laplace's equation, and then for this one in 2018 for biharmonic boundary value problems. So what we have done is that we have this expression here and this expression here for the rotated contour. So which means that if I'm given like a polygonal domain, like a triangle, so let's see, suppose that we have an analytic function in the interior of this triangle. So which means that we have the Cauchy integral formula. So suppose that this function is analytic in the interior. We have the Cauchy integral formula. Then we split this integral to a sum of integrals along each boundary. And now for each, so we have this representation for the Cauchy integral formula. So for each side, we are going to replace this Cauchy kernel by this exponential that I showed you in the previous slide. So for each side, we are going to replace this expression by an integral. So this expression here. So replace the Cauchy kernel for each side by this, and then chi j is the angle that each side makes with the real axis. And if we do that, then we find the following transform pair. So this analytic function h in the interior of the triangle is a sum of this rho j j k function multiplied by some exponential, and then there is rho j, this is called the spectral function, is the transform of the unknown boundary data along this respective side. So this is the transform pair derived in this geometric way. And so I should say here that this is a different way to derive the transform pair, which was which is done by Fogas and Kabaev using Lax pairs and Riemann-Hilbert problems. So it's so by basically geometric observations. So we have this transform pair for this analytic function in h in terms of these so-called spectral functions. And the idea is that if we can find this in some way, these functions rho j j, then we can put them back in this integral representation and then find our analytic function. And the way to find this function is by analyzing the so-called global relation, which says that the sum of all these functions, all these transforms along the boundary, is equal to 0 for all k in the complex plane. So this is crucial because analyzing this expression here will give us all the information that we want to construct these functions. So I should say again here that this representation is for this bounded polygon, but we can also find representations for unbounded and also multiply connected polygonal domains. And another thing is that this is a representation for a convex polygon. So if it's non-convex polygon, the idea is to split it into an atlas of convex subdomains. Okay. So that was a transform pair for a polygonal domain. So let's go one step further and consider how do we find a transform pair for a function analytic in a disk, for example. So suppose again we have a z dash point along the boundary and then point z in the interior, and we have this function h, which is analytic in the interior. So again we have the Cauchy integral formula given here. And now the idea is to write again a spectral representation for this Cauchy kernel, which in this case is given by this expression here. Was introduced by Crowd in 2015. So these are some exponentials which are decay along the integration contours. So this is L1, L2, and L3 is called the fundamental contour and is given in this figure here. So L1 is this the negative imaginary axis, and then this small circle. L2 is this one, and L3 is the contour in the positive imaginary axis. So again, we have this spectral representation for the Cauchy kernel. So what we do, we take this expression here and substitute it in there. So we get again this transform pair for the interior of the unit disk. So we have h of z is given here in terms of rho of k. Rho of k is a transform of the analytic function along the unit circle. So yeah, again, the idea is to find this function rho of k, put it back in your expression here, and then find your analytic function. And in this case, this function rho of k is equal to 0 for all k and negative integers. So again, this is what is going to give us all the information we need to find this function h. Okay, so you might be wondering why. So we have found transform pairs for a channel for a polygonal domain. We have found a transform pair for circular domains. So can we combine the two together? And the answer is yes. So for example, this geometry here, we have a cylinder in a channel. So suppose, I'm just going to go one step back. So if we were solving for an analytic function in a channel, we would be using Fourier transform. If we would be solving for analytic function exterior of a disk, we will be using Laurent expansion. But what happens if we want a transform method for a geometry which has both polygonal and circular boundaries? So these transform methods tell us that we can analyze problems of this form. So we have a cylinder in a channel. So we have this is a straight line. So this is like a Fourier type integral representation. Again, another boundary here, which is a straight line. So another Fourier type. And also we have the circular boundary, so which means that we have this Mellin type representation. So this expression here gives a representation for this analytic function h of z in this domain here, where these functions rho 1, 1, rho 3, and rho 2, 2 are given here. So these are Fourier and Mellin type transforms of the boundary data. So yeah, so what we want to do again is, in this case, we have global relations which are given here, that the sum of these functions are 0 for all k real, and these are for the Fourier type, and these are for the Mellin type. So again, this is the idea, to analyze those conditions, those relations, to find these functions, and then go back, put them in your integral representation, and find your solution. Okay. So that was for this circular domain, which had cylinder and a channel. But in this talk, I'm going to focus on in viscous flows in channel geometries. And the first problem I will consider is this geometry here. So this is joint work with Stefan Llewellyn Smith. So we have this channel geometry. We have a pressure-driven flow, and we have this linear expansion of the so the flow here is you have the flow is U1, and then U2, and then U1 and U2 are related by flux conservation. So so we want to understand what is the effect of having this polygonal transition region. So we have 2 parameters to play with. This is the angle of this expansion, and also the channel ratio, H. This is H and H capital. So we want to compute the pressure drop as well as the flow in general because of this transition region. Okay. Yeah. So this is, let's go back. So this is a polygonal domain, so we can use our transform methods. But this is a non-convex polygon. So the idea is to apply the methods, we need to split the domain in convex polygons. So we have 1, 2, and 3, 2 semi-strips, and then this 4-sided polygon. So let's start. So domain 1, this is a semi-strip. All the boundaries are straight lines. So we can write this integral representation for this. Remember that we are solving Stokes equations, and to solve these problems, we need to find these 2 functions f and g. So for these 2 functions f and g, which are analytic functions, we have these representations where f1 of z, for example, here is a sum of integrals of these spectral functions, and then these spectral functions are the transforms of your data along side 1, side 2, and side 3. Same for g. So we want to find these functions. So if we can find rho j and rho j hat, we can put them back here, find f and g, and we have solved the problem. So the way to find those functions is by using these global relations, which says that the sum of them, of this rho j, is 0, and the sum of rho j hat is 0 for all the k in the upper half plane. Okay. So again, so that was for domain 1. In domain 3, again, it's a semi-strip. We can write again an integral representation. Similar form. And then let's go to domain 2, which is this given here. And so the idea here is to use logarithmic map given here to map this geometry to this circular domain here, where basically, let me just go back. So here we have no slip boundary conditions along the boundary. So we will impose the conditions here and here. So it will be helpful for us to have these 2 boundaries being translated to being parallel. So this is what we are doing here, using this mapping to transform this domain to here, and then this boundary here corresponds to the upper plate, and then this one to this one here. And then what we do is so this is the z plane, the physical plane, and this is the eta plane. So what we do is we introduce these composite functions, f2 eta and then g2 eta. So if we can find these functions in this geometry, then we can go back and find them in the physical domain. So let's introduce these spectral functions, Sj of k, that this is the transform of f2 alongside, so we have side 1, 2, 3, and 4. So these are spectral transforms of the functions along each side. And then again, these functions satisfy the global relations. which says that the sum of them is 0, but now for these are valid for all k, for all complex numbers, because this is like this is a bounded domain, and for bounded domains this is the domain of validity of these global relations. Yeah. So basically what we have done, so we started with this domain, which was non-convex. We split the domain into 3 convex polygonal domains. And in each of them, we wrote an integral representation for the analytic functions f and g that we are trying to find. So what we are going to do next is, for each subdomain, we will be analyzing the boundary conditions that we have, so that we can find relations between these spectral functions, rho j, sigma j, etc. Yeah, so for each sub-problem, we use the unified transform method to obtain relations between these, the transforms of the unknown data on each side. And so what we do then, we use these global relations, which, as I mentioned, are crucial to give us all the information that we need to find these reduced number of unknown spectral functions. So we find these 3 relations here. And then you can see that, so this comes from analysis in subdomain 1, the semi-strip, and that is valid for all complex numbers in the upper half plane. Then this equation here comes from analysis in this bounded polygonal domain, and then this comes from analysis in domain 3. So you can see that you might recognize these expressions here. These are the spectra of this problem. So these are the so-called Moffat-Eigen relation. And then this corresponds to the odd eigenrelation, because the flow is symmetric with respect to the channel center line. So what we have here is that we have this expression here. So rho 1 is a transform of our function f along the lower boundary of the channel of the semi-strip, and then the right-hand side, W1, in all 3 cases, the right-hand sides, W1, W2, and W3, contain unknown boundary values along these vertical edges, which were coupling the 3 sub-problems, and also known quantities. And you see that these expressions are valid at these subdomains in the complex plane. But these expressions in front of these spectral functions have roots in the complex plane. And in this case, so this expression here, this eigenrelation here, which corresponds to the Moffat eigenrelation for theta is equal to 0 for the channel. So this has roots in the upper half plane, given by these blue dots here. So this is a k-plane. H is the channel height. So these are the roots where this thing is 0. But then this is analytic in the upper half plane. This is if we divide this expression by that, this blows up at those points, which means that we must insist that this function W of j, W1, vanishes at those points. Same for, yeah. Okay, same for this expression here. This vanishes at those black points here in the entire complex plane. This is analytic everywhere in the complex plane. So which means that the right-hand side must vanish at those points. And similarly for this expression here. So what we have that W of j, the right-hand sides must vanish at those points. So what we do is, and let me emphasize again that the right-hand sides contain the unknown boundary data along the vertical edges, which are connecting the three subdomains, plus known quantities. So what we do is we represent these unknown data along these vertical sides by Chebyshev expansions or other series expansions. And I know people in the who have been working on the Fogas method have used different choices of basis expansions, but here our emphasis is to show you the method. So we found that using Chebyshev expansions gave us good accuracy. So we have these representations for f and g, and we want to find these coefficients am and bm. So what we do, we take these, we go back here in the right-hand side, substitute those expansions, and then formulate a linear system. Basically, these equations, we are evaluating these the right-hand sides at those points. These are force conditions in this spectral k-plane. So doing that, we get a linear system composed of these three set of equations, saying that W1 is 0 for those points in their respective points, for each of them is different. So these are in the upper half plane, these are everywhere, these are in the lower half plane. Yeah.
How is S some transform function of K or what?
Yeah, so it's like the parametrization of the contour. Yeah. Yeah. Yeah, so formulating this linear system, we can compute the coefficients, these AM and BM coefficients. And then once we have that, we have them on the vertical edges. We can just go back, and by back substitution, we can find all the spectral functions, put them back in our integral representation, and we can compute quantities of interest, like the velocity, the pressure, vorticity. So here, I'm just going to show you some results. So here, yes.
Sorry, can I ask a question?
Yeah.
Where's the forcing term in that system of equations?
Yeah. Yeah, so basically, these functions here have unknown things and known things. So when you, yeah, so they appear, so this is, you have the right-hand side. Yeah. And the thing is that because we consider a pressure-driven flow, and in the two semi-strips, the boundary conditions are already satisfied. It doesn't appear in W1 and W3, but it appears in the transition region where the boundary conditions are not satisfied. Yeah. Yeah. So here I'm computing the pressure drop along the center line between these the ends of this transition region. So this is for function as a function of this channel height ratio for a small angle. And here we are comparing against lubrication theory that we expect to be accurate because it is valid for small angles. And then here I'm showing again the pressure drop between the two ends of this transition region for fixed for different channel width ratios and as a function of the angle. So you see that for small angles, the two methods agree as expected, but for larger angles, the lubrication theory fails. So we expect this new method to be accurate. Okay. So that was the first problem. I'm going to talk about this problem. So if you remember in my first slide, I showed you this polygonal domain, like this one here. So we are interested to, again, try to model flows in these channel geometries. And all these are motivated by biological applications. So I'm interested to solve these problems in this geometry. So let's just first consider. Let's just zoom in this region here and consider what this channel geometry here, and let's try to understand what is the effect of this corner transition. Okay, so if you remember in the previous problem, when we had this linear expansion transition region, what we did is that we used this conformal mapping, this logarithmic conformal mapping, to transform the angled boundaries to being parallel. So what we are going to do here is the same idea, because again, so this is a non-convex polygon. First step is we want to split it in convex subdomains. And what we do, so this is a corner here. So because it's a corner, we don't want to have, we want to transform this boundary here to be parallel, so that we can use a unified transform method. So because we have transform pairs for polygonal domains, we have transform pairs for circular domains, so it means that the splitting of the domain, we have the freedom to split it as we like. So in here I'm using this circular domain decomposition. So what I'm going to do, so we have 1, 2, and 3. So domain 1, this is like a semi-strip. It's not it's a semi-strip, but the third edge is a circular boundary. So domain 1, we say that F is Fs plus F1, G is Gs plus G1. Fs and Gs are the forcing, it's basically the background flow, and then F1 and G1 dashed are the analytic functions that we are trying to find. So in this case, we had straight line edge, circular edge. So this is Fourier type for the lower side, Fourier type for the upper side, and then Mellin type for the third edge. And these rho 1, rho 3, and rho of k are given here. This is like the Fourier type transform of your function f, Fourier type for rho 3, and the rho of k Mellin type transform because of the circular boundary. And in this case, the global relation is given here. Rho 1, rho 2, and rho 3 is equal to 0 for all k in the in the lower half plane. So notice that in this expression here, we have rho 1, which appears in the integral representation. We have rho 3, which appears here. Rho 2 does not appear here. Rho 2 is a Fourier type transform of your data along a circular boundary. So if we want to compute this expression here, we want to find this rho of k. Rho of k is a Mellin type. But the idea is, as we will show, is that once we find the boundary data along the boundary, we can compute both. So we can just go back and find our function. So this is representation for F1, but we can also find representation for G1 dashed. So I'm not having this here, but yeah. So that was for domain 1. Domain 3, same idea. It's like a semi-strip, but the third edge here is a circular shape. So we'll write a similar representation to this expression here. But for domain 2, we have this shape here. So what we do, we introduce this logarithmic map to map this circular domain to a semi-strip. And this is polygonal domain. So it's easier for us to analyze the problem and write, again, integral representation for a semi-strip. So we are transforming the problem from the z plane to the eta plane. And we introduce the composed functions f2 and g2. And then, so this is a semi-strip. So we have f2 is a sum of integrals which are all Fourier type because all boundaries are straight line edges. So yeah, so sigma 1, sigma 2, and sigma 3. So this is transform of your Fourier type transform of your data along the lower side, vertical side, and on the upper boundary. And then again, global relation is now valid for all k in the upper half plane. So the idea is you are given a domain, split your domain in convex subdomains, and you have the availability of these transform pairs for polygonal domains or circular domains. Combine the two to write down your integral representation for each of the domains, and then next step, try to analyze each sub-problem, your boundary conditions, using the unified transform method to find relations between these functions, all these functions here, find relations between these functions, also find relations between these functions, and then these relations will combined with the global relations can give you some conditions, which now we have giving here. We had 3 subdomains. So for each subdomain, we have, again, some conditions. Now notice that we have, because the flow in, let's say, domain 1 is not symmetric, so we have both odd and even eigenrelations here, so like the spectra here. And so that is found by analyzing the problem in domain 1, this semi-strip with a circular boundary. Domain 2, this corner domain, and domain 3, we get this expression here. Then now, again, W2 and W3 contain unknown boundary values along the common edge, like basically the vertical boundaries, because it's we have transformed the common edge to be a vertical boundary. And yeah, so these contain known quantities and unknown boundary values. And what again want to do is to exploit the analyticity properties of these functions to identify special points in the k-plane, which we can use to formulate a linear system. So here in this figure, I'm showing some of those points. I'm only showing this one, these points here, and this, because the problem is symmetric with respect to the center line. It's sufficient to analyze just the problem in just domain 1 and 2. So this is not needed. Yeah, so basically what we do, it's the same idea, is to represent our data along these common boundaries using, again, Chebyshev. I used Chebyshev expansions for that. Put everything back and formulate a linear system which is composed of this. Sorry, maybe. So this is not quite right. So I'm saying that this numerator here must vanish at zeros of this expression here. This must vanish at zeros of that. This at zeros of that. And if we do that, then again we can compute the coefficients, and then go back and find all the quantities of interest, like the velocity, pressure, so whatever we want to compute, either on that boundary or in the interior. Here I'm just showing some streamlines for velocity for along that boundary that we are solving. I'm not. Yeah. Just go. So yeah. So that goes for. We zoomed in this region here, but same ideas. We can analyze more complex problems, trying to understand what is the effect of having this transition, this more complicated polygonal domain. So here if we consider this Z-shape geometry, domain 1 and 2, we already have the. So basically, you only need the analysis in a semi-strip geometry, or in this, in this geometry we have parallel lines. So you only need two components, this domain here, and then this which appears near the corners. So yeah, so again, if we also want to do, trying to understand what is the effect of having two corner regions, we can again consider this thing split in convex polygons, and for each of them, write your integral representations and try to compute the functions, and then once you have the function along the common boundaries, you can construct everything in the interior, all the quantities that you need. Okay, and then the last problem, I'm not going to get into details about this problem, but I'm just going to mention this problem, which is Stokes flow in a channel with an angled plate, and this problem is motivated again by biological applications. Yes, pressure-driven flow. This you have a plate of finite length and located anywhere in the channel, and yes, so this is any angle. And this problem has been analyzed for theta is equal to 0, which means that if the plate is parallel to the channel walls, this problem was solved by Kim and Chang using a 3-part Wienerhoff method, and also for the case of pi/2 by Yoon and Jong, where they used, if I remember correctly, eigenfunction expansions. So this method that I presented is ideal for solving problems where you have angled boundaries. So I'm sure now you can see how to. So this is again this is a multiply connected domain. It's non-convex. So what we want to do, we want to split it in convex subdomains. So just do that. So semi-strip, this polygonal domain, and then again a semi-strip, and then for each of them, find your integral representations. If we have angled boundaries, the idea is to use this logarithmic map to transform your boundaries, the boundaries where you have boundary conditions, to be parallel. And the idea again here is we want to find representations here. We use logarithmic map to map it to like a domain where the upper and the lower boundaries are mapped to parallel boundaries. And yeah, so this is still a work in progress. This is joint work with Stefan Llewellyn Smith and Sarah Waters. Yeah, so let me summarize. So I have showed you how to solve problems using the unified transform method, also known as the Foucault's method. So the method is can be used to solve problems in convex domains, but also if the domain is non-convex, you can just split into convex subdomains and impose continuity along common boundaries. So yeah, for the problems I showed here, we had the new idea was we had these geometries where we had angled boundaries. So the idea was to use a logarithmic map to transform the angled planes to parallel boundaries, and then analyze the problem in this transform parametric plane. So we consider this as a quasi-analytical solution because, in general, you only need few terms in those expansions to give good accuracy about the solution. And then once you have these coefficients, you have closed form expressions for all the quantities that you need. I mean, you still need to compute them numerically, but they are closed form expressions. So these are, so these methods can be applied to solve complex general geometries. Here I showed you only polygonal geometries. Only the last problem was multiply connected, but you can also use it for multiply connected circular domains, or you have, having those transform pairs for polygonal and circular domains, you have many tools to analyze these problems. Okay, thank you very much.
Thank you very much. Yes. So it seems like you have a lot of freedom, I guess, in picking how you split the convex domains into subdomains.
Yeah, yeah.
How do you pick which one is the best? I mean, that would work.
Yeah, so you have freedom to choose as you like. In general, you try to. So my idea is if you have angled boundaries, you try to transform them in this, having them parallel. So you try. So you try to split the domain in as little subdomains as possible, and also try to have parallel domains. Domains with parallel boundaries.
Okay, because that kind of, so one of the,
yeah.
Can you go back to the corner geometry one?
This one or?
That one's fine, I guess.
Yeah.
So why not do, for example, I mean, just rectangle, 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 or rectangle?
Yeah, you can do, so for example, you can do like a rectangle here, right? So if you do a rectangle here, it's just, let me just go back. I have the figure. So if I'm doing a rectangle here, if I use a logarithmic map, this will be mapped to not a semi-strip, but something which has like a different circular shape. So you can do both. So if you remember, if in the previous problem, this one here, we just split it in these straight line edges, and here it was circular. So you have the freedom to split as you like, as long as the angle boundaries are mapped parallel to each other. Yeah. Thanks.
So Fourier methods and methods based on cross integrals have a nice property that it makes it easy to compute the real piece of the time.
Yeah.
Does this approach inherit this property?
Yeah, yeah. For
Just bring down half K.
yeah. So for example, if I want to compute the pressure, let me go. So let me just give this one here. Pressure, for example, which is the real. Sorry, let's go back. Pressure is the real part of that for F dashed, and then F dash, for example, for, let's say, this problem, F dashed is K appears only there, so just IZ rho JK.
In my problem that I showed up like solitary waves over a forked region.
Yep.
First exercise I did, so it's very nice. It shows this. It was a solitary wave making a sharp turn like your L. And I used the Stoffel mapping to do it. But it had already, we were already called thing that had a ring. When the wave passed by, there was a little bit of ringing in the sort of the intrusion corner that comes in. Right? And we got around it. We did a nice thing, actually, and it worked well.
Yep.
Now your sort of domain decomposition, if I may call it,
yep.
is very interesting with this circular region. And what it seems like it's somehow, in my mind right now, like hiding, or not quite hiding, not finding the right word, with this singularity that's done by the intrusion, which is a natural sort of singularity. So
yeah.
What's taking place here with this sort of circular region, which is kind of nice? Probably if I did a solitary wave passing by, I think I probably would have less ringing. I don't know, I'm trying to guess.
Yeah.
What does it do with the intrusion singularity that comes in when you do this?
Yeah, so the reason that I've thought of this splitting is because near this corner you have the Moffat eddies forming because it's a 90 degrees. So here and here you have different behavior, like so different singularities. So splitting the domain in this subdomain here, and using this mapping, you are avoiding. So basically, if you see here, this denominator here, this is takes into account what happens near the corner. So, but without going close to the corner. So basically, you have this circular domain here. The origin is mapped to infinity, and in some way, the method takes account what happens at those points. Yeah.
Yeah, that's right.
Yeah.
It works very well for your case. Okay,
Yeah.
It's a different flow. Mine is in
Yeah.
is a wave flow and so on. So
Yeah.
Okay. Thank you.
So as a numerical guy, can you give us some information about convergence rates?
Yeah.
And for example, there are these singularities that you mentioned. So how much work does it take and how fast does it converge?
Yeah. I can give you both the first problem, for example, this one here. We used Chebyshev expansions, and I think we used maybe 16 modes. And so here is comparison against lubrication theory. So I think the 16 modes, the 16th mode was 10 to the minus 7 or 10 to the minus 6, something like that. So we have freedom to use different basis expansions. So I know, for example, Matt Colebrook has been using these tailor-made basis functions with taking account of the singularities. So so I haven't done extensive study of the numerics, but before trying Chebyshev, we tried Fourier type, and then you see that, okay, obviously Chebyshev is much better than Fourier type, and I don't know. I mean, maybe you can make this. You can improve this. Yeah.
I mean, just on that question of numerical analysis, this is a fertile area for numerical analysis as far as I see. Stochasters been leading for the last 15 years. Various people studying aspects of it. I think it's still very unclear. It's an interesting method because it kind of sits in the middle of spectral theory and boundary integrals. Because you see the spectrums coming out if you manipulate the global relation, but you don't actually use any eigenfunction expansion. You can use whatever you like. But in my experience of using this method, not just, you mentioned some of my work earlier in this, I noticed that if you weren't careful, you could end up with highly incomplete condition systems. So there's a lot of work to be done to pin these issues down. When it works, it's fantastic, and it looks better than other methods. For example, here, you notice a lot of these were semi-infinite domains with corners. These are all cases where boundary integral methods have trouble, and you have to do all kinds of tricks to get around it. But these are, in a sense, suited to those types of problems.
Yeah. So you're just using the parameters that you have, A1 and B, truncating it, and you're matching, making sure that you have the zeros in the right places of a finite number of them.
Yeah.
So what is the effect of the one, because you're truncating at some stage, but you're not matching the ones which are farther off in the complex K plane.
Yeah.
So do we know what the effects of those are?
No. Not from what I've read. But people have been saying, you should probably talk to Matt. I think he's done the most recent work. Matt, yeah?
I think it's not.
So could you, for instance, look to, there's a, for meromorphic functions in general, there are product form representations where you could place zeros in some places and take care of the zeros that come up exactly, and then whatever remains, put it in that format. That way you don't have this problem.
This is a very important point. You somehow want to get the infinite ones you're listing out somehow right.
Yeah.
Approximate.
Yes.
So the last problem about the plane. So when you split it into convex domains, there will be singularity one half. I don't see how you can recover it.
Yeah. So that.
Single integral equation with channel that you unbound integral method give you immediately singularity one half. But when you split it and do all these chills and stuff,
Yeah. So.
how do you find this one half?
So here, I mean, yeah, as you mentioned, this point you have this square root singularities. So we're still working on this, but when we will expand on those edges, we will put the singularity, we will use a basis expansion, which will have the correct singularity at that point. Yeah.
Another question about matching. So
Yeah.
when we use this, if you're splitting like circle, semicircle, and quarter circle, and then the rest is not really convex domain, it's
Yeah.
concave. I don't know how the method works with the rest. But then you map it in the half a strip. So you match half strips with the half domain?
I'm mapping the data along the edge of finite length. I'm not mapping everything on all sides. I'm only mapping. So basically, the idea, the reason that we are transforming on this semi-strip is because if you try to play with your equations in this semi-strip geometry, you just end up with conditions on only the third edge, like the edge of finite length. So you're basically only matching the information on that edge and not everywhere else.
Yeah, but
Yeah.
you need to match the external
Yeah. So
domain, right? So you use conformal mapping and you use, you match the data after mapping with the previous.
yes, yeah.
By the new mapping, like logarithm functions, they shifted, and then there is discontinuity.
Yeah. Anyway, this sounds a bit technical, and we've run out of time, so let's thank Elena again. And